So now at last we come to the concept that we've mentioned in terms of muscle physiology, which is the action potential. And the action potential is actually a very well-known phenomenon. You probably heard of it before this class. An action potential is a brief, large reversal of membrane potential. For example, going from -70 all the way past 0 to +30 millivolts. Specific voltage-gated channels will open in a particular order. This only happens at the axon. This is an all or none phenomenon. In other words, it is not decremental. It does not decay the way that a local potential or a graded potential decays. One of the ideas of an action potential is that threshold must be reached in order for an action potential to begin. Okay, I want to first of all bridge the previous lecture and show you how they're actually this is actually tied to this phenomenon is tied to the previous lecture. You will recall that when we talked about local potentials, they happened inside of the dendrite, for example, or possibly along the soma, and that they were able to pass, and if there was a specifically strong current or a strong stimulus, that current might actually pass some distance. So where does it start to matter? Well, it starts to matter at the axon hillock. You may recall that I talked about the axon hillock being possibly the most important part of the neuron because the decision is made at the axon hillock whether there is enough signal to allow for communication in the form of an action potential to take place. So what do I mean by enough signal? Enough signal means enough of a local change taking place inside of the dendrite or taking place inside of the soma. If there's enough signal, if there's enough stimulus entering here, where enough sodium ions, for example, are entering the cell and allowing for a depolarization to occur, that actually reaches all the way to the axon hillock, then it's very likely that this is enough signal to allow for an action potential to occur. So then it's easier to see then the idea of threshold and the significance here. Threshold is defined as a number that is cell specific, that is specific to a particular cell's character, that is usually 15 to 20 millivolts over the resting membrane potential. So if our hypothetical cell, the resting membrane potential was -70, threshold was -55. And in order for an action potential to occur, you have to get to -55. How do we get to -55? That signal comes from the local potential, from the graded potential that occurred way back in the dendrite or way back in the cell body. So now when we think about the beginning of an action potential and how the thing is generated in the first place, it's important that we note that our microelectrode here, we're measuring what's happening inside of the axon hillock. If it doesn't happen in the axon hillock, it will not happen along the rest of the axon. All right, so let's look at the steps of an action potential. And I think the best one to look at is actually probably this picture. Again, draw your resting membrane potential versus time graph and draw your threshold, draw your numbers, -70, -55. Go ahead and draw 0 and +30. Draw your time in milliseconds, but this time make it only 4 milliseconds total. It's a much shorter time course. Okay, so the first number 1 here is called rest. What happens during rest is that all of the channels are closed and nothing is changing. No ions are flowing in or out at any significant level. You probably have some potassium leaking out. You probably have the sodium-potassium pumps working. However, there's no net change taking place, so it stays at -70. The depolarization phase of the action potential, number 2 here, what occurs here is that sodium channels are opening. And the sodium channels that are opening are voltage-gated sodium channels. Sodium, as a result, will rush into the cell, causing a huge depolarization, a huge upswing in your membrane potential. And then number 3 here is the repolarization. What happens during the repolarization stage is that sodium channels are closing and that potassium channels begin to open. And as a result, potassium rushes out of the cell, and since it's a positively charged ion, that actually kind of subtracts from the positivity inside of the cell and makes the inside of the cell more negative. And so the inside of the cell repolarizes back downward. And number 4, the 4th step here is called hyperpolarization. The sodium channels are completely closed at this point, and the potassium channels are still open for a period of time that allows for more potassium to leave the cell than is even necessary to establish a resting membrane potential, and it eventually gets back to rest. But it kind of overshoots rest, so it's called a hyperpolarization for that reason.